Hello, everybody. So welcome back. I want to move on to section 3.3. Section 3.3 also includes a bit about Cramer's rule, although Cramer's rule is terribly inefficient and only saves you errors in programs very situationally. So we're going to skip that. There's also a bit in there about calculating inverses, combining determinants with the adjugate matrix, which is a nice trick computationally, but also not terribly important for our purposes. So I'm going to skip over that as well. And instead, I want to focus on a little bit of geometry, in particular how determinants relate to things geometrically when we talk about transformations and vectors. So first, to motivate ourselves, I want to look at the 2x2 case. So 2x2 matrices, or transformations, linear transformations that go from 2 dimensions to 2 dimensions. And our motivating question here is going to be, say I'm given one of these 2x2 matrices, which we would normally write A, B, C, D like this. The first question I want to look at is, if I look on a set of coordinate axes, so say here's X, here's Y, let's look at these column vectors. So let's say here's my AC, and then let's say here's my BD. Now, something that works out quite nicely is if I wanted the area of the parallelogram determined by these two vectors. So I just take another copy of AC right here, and I put it up here, and then I take another copy of our BD right here, and I put it over here. This forms a nice parallelogram, and the first question I want to ask is, what is the area of it? Now, one trick that'll help us that some people may be familiar with is if I want to take the area of a parallelogram, and I take two of them that live within the same parallels, or between the same parallels, so say this rectangle right here, if all I do is take the top here and shift it or skew it over to one that lives within the same parallels but has the same base width, then these two will have the same area. If we just skew it over like that, it won't change the area. And so that's a useful piece of knowledge that we'll use to try to do this a little more easily. The other bit is, to do an area of a parallelogram, we need a base and a height. And it's a little easier to get a height if I didn't have this thing skewed upward at all. So the first trick I'm going to use is, we're going to imagine, parallel to the x-axis, cutting this top piece off of that parallelogram. So we're going to remove that from the top and instead extend this side over here down to the x-axis and add this bit on. So now we're finding area of this parallelogram, which will be the same because all I did was take a piece off and move it. And we already know the height, because the height of this thing is just going to be the y coordinate of my BD vector. So my area, which is, let's say, height times base. Well, we already know the height. The height is the y coordinate of this vector here, so I already know that's a d. And now we just need, what's this base? Now, my base isn't actually the x coordinate of this vector here. It's not a, because that would be the x coordinate of this vector, which would be down here. And this is not a right triangle. This side here is tilted in. So we have to be a little more careful than that. What I really want for my base is this length right here. And the easy way, not inventing new techniques that you're not familiar with yet, to do that is, really we just want to know, where does this line cross the x-axis? that'll give us our base width right here. So my first question is, what is that line? Well, I have a point that's on the line. This AC point is on the line. So I have a point that's on the line. And I also know the slope of this line because this side here is just a copy of this BD vector. And it goes up by D as it goes over by B. So that means my slope is just D over B. And okay, so that gives me an equation of a line. I have a point and a slope. So y minus the y value of the point equals slope times x minus the x value of the point. And that says my line looks like this. So here's that line. Now where does the line cross the x-axis here? Well, that's just when y equals 0. So set y equal to 0, and I've got minus c equals d over b times x minus a. What does that make my x? Well, let's divide that d over b off of everything. So that would give me divide by d over b, divide by d over b, and that would give me negative bc over d equals x minus a, and then just add the a over. So we're getting x is a minus bc over d. Okay, so that's the base of this parallelogram. So the area of this parallelogram, a minus bc over d. Oh, well, this is quite nice because that d is going to distribute. And so what does my area come out as? AD minus BC. So what that tells us, if we come back over to here, the determinant of this told us the area of parallelogram. I'm clicking too much. Let me switch back to my regular handwriting. Determined by those two vectors, AC and BD. Now, a natural question is, well, our determinants can come out negative. And, I mean, area can't be negative, so what's going on there? What does the negative on the determinant represent? And that's really important because actually what I've written here is not quite true. What's really true is that the absolute value of the determinant is the area of that parallelogram. Now let's look at what does a negative in the determinant actually tell us? When would that happen? And it turns out the negative in a determinant would look like, say I had these two vectors, but in my matrix here, let's say my first one, what we would had as our AC, and what we had over here is our BD. Let's say the first vector is not this one, it would be this one up here. And the second vector is this one down here. What that means is that this transformation, as a transformation, if I multiply this on some x vector and see where it goes, this transformation sends my first coordinate vector to AC, by the way we define what these transformations do off the matrix, and it sends the second coordinate vector to BD. In other words, my original sort of unit square with those two coordinate vectors, this one's getting sent up here and this one's getting sent down here. So what that tells us is that the order of them, if I go around clockwise, got swapped. There was a switch. And another way of thinking about that is that, oh, this transformation looks exactly like the old one that we drew a picture of, except what happened in our two vectors here is, well, now this one was my second column, this one up here was my first column. So we could have thought of this as, oh, same as the old one, except we swapped columns. And of course, a column switch, just like a row switch, makes a negative determinant. So what's happening here is that negative determinant signals a reflection, if we're thinking in terms of the transformation given by that matrix, a reflection, or if you want to speak more mathematically, we call this a change in orientation. If I imagined looking on the plane here and drawing, let's say, a little arrow, something in my linear transformation happened that when I apply that transformation, or left multiplied by that matrix that gives that transformation, that swapped the direction of these things around somewhere. So that sort of thing is what the negative on the determinant is signaling, which can be quite useful information, but I want to focus more on the area. So one thing that this does is this gives us a nice little trick for calculating areas of triangles. So for instance, let me write an example here. Okay, so what this question is asking is, it's just giving me the corners of a triangle. And it says, what's the area of this triangle? So let's see what that looks like. So I have 1, 1. So here's one corner of the triangle. Then I have 3, 2. Here's another corner of the triangle. And then I have negative 1, 3. So let's make my picture a little bit longer. Negative 1, 3. So it's saying, what's the area of this triangle? And now the point of this exercise is we can use that idea that we have a nice trick of taking the area of that parallelogram using determinant. Problem is that parallelogram is coming up off the origin. So first what we need to do is I need to move one of these corners to that 0, 0 point. And so I will move this 1, 1 point to the origin, down to here. So I want to shift my whole triangle. Now how do I do that? Oops. Well, if I want to move this point to the origin, that shift just means if it's going to 0, 0, that means I subtracted it off. So that one moves to the 0, 0. This one, if I subtract the same thing off, we want to shift the entire triangle. Then I'm getting 3 minus 1 is 2, 2 minus 1 is 1. So it's going to move to that point. And this one, if we subtract the 1, 1 point, we're going to get negative 1 minus 1 would be negative 2, 3 minus 1 would be 2. So these are my new points. So my new triangle is going to look like 0, 0, and then I have 2, 1, so 2, 1, and then I have negative 2, 2, so negative 2, 2. So my new shifted triangle is going to be this one. And so I can actually think of this 2, 1 point and this negative 2, 2 point as this vector here. So there's 2, 1. And this vector here, so there's my negative 2, 2. And now the parallelogram determined by those vectors, which would look like this box, the area of that is going to be given to me by the determinant of that matrix formed by these vectors. So let's say 2, 1, negative 2, 2. And now, remember though, the determinant can come out negative. We only care about area. We really want the absolute value of the determinant. And now this is the area of this whole box here. And so if we wanted the area of that triangle, well, my triangle is exactly half of that box. So really the answer to my question is 1/2 of the absolute value of this determinant. And so then if I want this area, we'll just finish calculating this. So I have 1/2 absolute value of 2 times 2 minus -2 times 1. So that would be -2 times 1. So we're getting 1/2 absolute value 4 minus -2. So 1/2 of 6, or 3. So the area of that triangle is 3. Now, this idea of determinants as area relates to the linear transformations even a little more strongly. Now, we have that idea that the negative determinant signals a change in orientation. Rotating around the origin is not a change in orientation. So if I have a linear transformation, so let's say t is a counterclockwise rotation by some angle, let's say theta, about the origin. Then what's the matrix that gives that transformation? We had a formula for that. So i.e. our matrix would be, what was the formula for that? That was cosine of that angle, and then sine of that angle. And then my next column was negative sine of that angle, cosine of that angle. So my transformation would say I started out with this object here, then I would just be rotating it around the origin counterclockwise by some angle, and I would get a new shape here where if this potato is smiley this way, it ends up smiley this way, and it doesn't get reflected or anything strange like that. Notice that the determinant here is cosine times cosine, so cosine squared, and then minus negative sine times sine, but that would be minus negative, so plus sine squared. And that's the same angle here and here, so this always just equals 1. So there is no change in area if I'm just spinning my plane around, and there's also no change in orientation, so the determinant comes out positive as well. So we have to be careful when we're thinking geometrically. Am I actually changing the area? Otherwise my determinant would only be 1 or -1, and as long as there's no reflection or any kind of swapping of that kind, my determinant would also stay positive. And this also gives us other tricks we can come up with for computing areas. If I know the linear transformation that, say, takes me from this circle to, let's say we stretch horizontally and we make this ellipse or something like that, and I wanted a formula for the area of the ellipse or an area of a specific one, if I knew the matrix for this transformation, remember that determinant tells me that unit box is getting sent to some parallelogram that's going to get skewed. And so if I imagine chopping this shape up into those blocks, then the determinant tells me the area of those blocks that my unit square gets transformed into. So if I imagined approximating areas by breaking it up or whatever, each piece inside of this shape is going to get skewed in exactly the same way as the determinant tells me. And so that tells me the area of the new shape after the transformation is going to equal that absolute value of the determinant times the area of the original shape. And this is quite nice. So you can do things like derive very easily areas for ellipses and some other basic shapes using that kind of trick. But we won't bother with that. So now I want to go up in dimensions and talk about 3x3 matrices, or transformations that go from 3 dimensions to 3 dimensions, because this is a bit interesting. So let's talk about what the determinant tells us. So we have some matrix, let's say A, B, C, D, E, F, G, H, I. Then the determinant actually behaves the same, except now we have 3-dimensional volume instead of area. So the absolute value of the determinant of, let's say, this matrix is the volume of the, I can never spell this word, parallelopiped. I don't know how to pronounce it either. I'm just going to call that the skewed box, determined by the 3 vectors. So what do I mean there? I mean that, so let's draw a picture of what I mean by this skewed box. So I have these 3 vectors. We imagine we're in 3-dimensional space now, and I have these 3 vectors coming off the origin. What is that skewed box determined by them? Then, so what that means is I have these 3 vectors coming off the origin. Let's say I have these 2, which are going to determine some base on the bottom. So the base of this parallelogram would look like this. I get another copy of those 2 vectors attached to each other. And then I have this 3rd vector coming up, say, that shows me how much this box is skewed this way. And now I'm going to get something that looks like see, another copy of this guy would be here. Another copy of this one would be up here. And we're going to end up with the box that looks like this, where these are the 3 vectors that form the columns of our matrix. So the absolute value of the determinant of that 3x3 would give me the volume of this box. Now, this also connects to everything we did with 2x2s. So absolute value of the determinant can also tell us how much the transformation, let's call it T of x equaling left multiplication by that matrix, skews area, or not area, sorry, volume. So if I take, say, some box or a sphere or some kind of 3-dimensional shape and I apply that transformation from R3 to R3, it'll tell me how much the volume of that figure is going to change after that linear transformation, which can be handy. And then also it gives us a trick for tetrahedra. So I like this sort of computation. So let me write down an example. Okay, so here's an example, and it's asking us to find the volume of the tetrahedron whose vertices are these 4 points. So this is an interesting geometry question that if we didn't know our linear algebra would be a huge pain in the butt to solve. What it's asking is if I just give you the coordinates for these 4 points in 3-dimensional space, what is the volume? Of course, this side wouldn't be visible. So what is the volume of that tetrahedron, that pyramid formed by them. So given any 3 points, or 4 points, sorry, what is the volume of that shape that you get? Sorry, I was missing a line over here. So kind of like a 4-sided die, except these things can be very skewed. We're given 4 points in space here, and we're saying, whoop, what is the volume of this pyramid that we get? That one's really skewed. And so how do we solve such a thing? And this is a really nice trick, very handy, because trying to use more basic geometry, distance formulas and the like, to solve such a question is a huge pain. And so in general, I just wanted you all to know this because it's handy. So same trick as before. We want to look at this as a piece of the skewed box, not a parallelogram anymore, that comes off the origin. Problem is, none of these points are the origin, so we need to shift all these points. I need to take my box wherever it lives, and I need to take one of the points and shift the entire box to where that one point, whichever one I want, lives on the origin there. And then once I do that, those other points will represent the other vectors that determine that box. So let's do this really quick. I'm just going to say, let's shift this first one to the origin. So that's going to go to 0, 0, 0. And then I'm going to shift all the other ones the same way by subtracting that point. So we're going to shift everything off until that point goes to the origin. Everything else is going to be moved along with it. So my new points are going to be 3 minus 1 is 2, C1, 3, negative 1, 3, 1, and then finally 5 minus 1 is 4, 4 minus 2 is 2, 2 minus 1 is 1. And so now I'm looking at the new box that's determined by these 3 points, and we'll get the volume of it. So we want absolute value determinant of, and we're using these as the columns now, so I've got 2, 1, 3, negative 1, 3, 1, and 4, 2, 1. So we want a determinant of this thing. And I'm going to do the determinant by, I'll just expand along the first row. So we want absolute value of plus 2 times the determinant of the submatrix by cutting out that guy's row and column, and then minus negative 1, which would become plus 1 times the determinant of the submatrix when we cut out that guy's row and column. 1, 2, 3, 1. And then plus 4 times the determinant of the submatrix I get when I cut out that guy's row and column. And so we've got absolute value of 2 times 3 minus 2 plus determinant 1 times the determinant of this matrix would give me 1 minus 6, so negative 5. And then plus 4 times the determinant of this matrix, which is going to give me 1 minus 9, which would be negative 8. And so finally we're getting the volume of that box determined by those 3 is going to be negative 8 times 4 would be minus 32. If I add this up, I've got, let's see, negative 3. So we're getting absolute value of negative 35 or 35. Now that was the volume of the box, so that's a problem because what we actually wanted was the volume not of this whole box, but we wanted the volume of just this tetrahedron that I get, this sort of triangular piece that fits in this corner. And now, what is the volume of that piece? Well, let's think about how it compares to the volume of that box. So here's my three vectors. The base, well, the base of this triangular piece here is half of that whole parallelogram, so you would just cut that in half. And so we have half the base as the whole box, but then also we have this pyramid shape. Now, in terms of volume, how does this pyramid shape relate to the entire box? Say if I took something with this triangular base, but then made the prism where I just took that height, but didn't have it narrow into that single point. And that's 1/3 of the volume of that rectangular prism. So let's see, 1/2, 1/3. It turns out that the volume of the tetrahedron, sorry, I'm going to switch my handwriting back. Oop. Tetrahedron is 1/6 the volume of the box. And so for the question we were trying to answer, that's 1/6 of 35. And so 35 over 6 turns out to be the volume of this tetrahedron here. Very handy. So that's as much as I want to cover from section 3.3. Thank you all.